Learning objectives. In this chapter, the user would learn the following aspects of techniques of connectivity and networking: interfacing, infrared connectivity, radio connectivity, controller area networks CAN, and local area interconnect network LIN, embedded system and internet. CAN, which was developed by Bosch in the early 1980s and became an international standard. ISO 11898 in 1994 was specially developed for fast serial data exchange between electronic controllers in motor vehicles. This is precisely how CAN can also be used in the implementation of industrial microcontroller networks. For example, as an internal bus in machine tools to interconnect distributed measurement, control, and monitoring functions on the lowest automation level to a higher level computer, or as a field bus to interconnect sensors, actuators, and or user interfaces. CAN is a multi-master serial bus standard for connecting ECUs. Each node requires a central processing unit or host processor. The host processor decides what received messages mean and which messages it wants to transmit itself. Sensors, actuators, and control devices can be connected to the host processor. CAN controller, hardware with a synchronous clock. Receiving. The CAN controller stores received bits serially from the bus until an entire message is available, which can then be fetched by the host processor, usually after the CAN controller has triggered an interrupt. Sending. The host processor stores its transmit messages to a CAN controller, which transmits the bits serially onto the bus. Transceiver. Receiving. It adapts signal levels from the bus to levels that the CAN controller expects and has protective circuitry that protects the CAN controller. Transmitting. It converts a transmit bit signal received from the CAN controller into a signal that is sent onto the bus. The PIC32 controller area network. CAN module implements the CAN specification 2.0b, which is used primarily in industrial and automotive applications. This asynchronous serial data communication protocol provides reliable communication in an electrically noisy environment. The PIC32 device family integrates up to 2 CAN modules. The figure illustrates a typical CAN bus typology. Overview of LIN. The Local Interconnect Network (LIN) bus was developed to create a standard for low-cost, low-end multiplex communication in automotive networks. Though the controller area network (CAN bus) addresses the need for high bandwidth advanced error handling networks, the hardware and software costs of CAN implementation have become prohibitive for lower performance devices such as power window and seat controllers. The protocol's main features are listed below. Single master up to 16 slaves, that is, no bus arbitration. This is the value recommended by the LIN consortium to achieve deterministic time response. Slave node position detection (SNP) allows node address assignment after power up. Single wire communications up to 19.2 kbits per second at 40 meter bus length. Guaranteed latency times. Variable length of data frame 2, 4 and 8 byte. Configuration flexibility. Multicast reception with time synchronization without crystals or ceramic resonators. Data checksum and error detection. Detection of defective nodes. Low cost silicon implementation based on standard UART or SCI hardware. Enabler for hierarchical networks. Operating voltage of 12 volts. LIN advantages. Easy to use. Components available. Cheaper than CAN and other communications buses. Harness reduction. More reliable vehicles. Extension easy to implement. No protocol license fee required. LIN is not a full replacement of the CAN bus, but the LIN bus is a good alternative whenever low costs are essential and speed or bandwidth is not important. LIN provides cost-efficient communication in applications where the bandwidth and versatility of CAN are not required. You can implement LIN relatively inexpensively using the standard serial universal asynchronous receiver or transmitter UART embedded into most modern low-cost 8-bit microcontrollers. Modern automotive networks use a combination of LIN for low-cost applications, primarily in body electronics, CAN for mainstream powertrain and body communications, and the emerging FlexRay bus for high-speed synchronized data communications in advanced systems such as active suspension. The LIN bus uses a master-slave approach that comprises a LIN master and one or more LIN slaves. To implement a LIN master or slave in hardware, all that is needed is a microcontroller with USART capability and a bus interfaced IC. Today, internet accessibility in one form or another, if not an a priori requirement, is at least a highly desirable option in many embedded applications. Internet connectivity, or in more general words, network connectivity for embedded systems, can be seen as an enabling technology for both current and future applications. Even today's low-cost microcontrollers are strong enough to handle a LAN controller, on-chip, off-chip, a communication stack, and usually multi-threaded applications. Having our embedded system with a fancy operating system is all well and good. However, embedded computers are worthless if they can't interface with the outside world. In computing, an interface is a shared boundary across which two separate components of a computer system exchange information. The exchange can be between software, computer hardware, peripheral devices, humans, and combinations of these. Some computer hardware devices, such as a touchscreen, can send and receive data through the interface, while others, such as a mouse, microphone, or joystick, are one-way only. Input-output interface. Input-output interface provides a method for transferring information between internal storage and external input-output devices. Peripherals connected to a computer need special communication links for interfacing them with the central processing unit. The purpose of the communication link is to resolve the differences that exist between the central computer and each peripheral. The major differences are: peripherals are electromechanical and electromagnetic devices, and their manner of operation is different from the operation of the CPU and memory, which are electronic devices. Therefore, a conversion of signal values may be required. The data transfer rate of peripherals is usually slower than the transfer rate of the CPU, and consequently, a synchronization mechanism may be needed. Data codes and formats in peripherals differ from the word format in the CPU and memory. The operating modes of peripherals are different from each other, and each must be controlled so as not to disturb the operation of other peripherals connected to the CPU. To resolve these differences, computer systems include special hardware components between the CPU and peripherals to supervise and synchronize all input and output transfers. These components are called interface units because they interface between the processor bus and the peripheral device. Input-output versus memory bus. The processor must communicate with the memory unit. Like the input-output bus, the memory bus contains data, address, and read or write control lines. There are three ways that computer buses can be used to communicate with memory and input-output. Use one common bus for both memory and input-output, but have separate control lines for each. Use one common bus for memory and input-output with common control lines. In the first method, the computer has independent sets of data, address, and control buses, one for accessing memory and the other for input-output. This is done in computers that provide a separate input-output processor, IOP, in addition to the central processing unit, CPU. The memory communicates with both the CPU and the IOP through a memory bus. The IOP communicates also with the input and output devices through a separate input-output bus with its own address, data, and control lines. The purpose of the IOP is to provide an independent pathway for the transfer of information between external devices and internal memory. The input-output processor is sometimes called a data channel. When memory and input-output devices are interfaced to a processor, either an isolated input-output scheme or memory-mapped input-output scheme is used. Memory-mapped input-output is one where the processor and the input-output device share the same memory location, while input-output mapped input-output is one where the processor and the input-output device have different memory located to each other. Isolated mapped input-output. The isolated input-output configuration separates all input-output interface addresses from the memory addresses. In isolated input-output configuration, the memory address and input-output address have its own address space. In the isolated input-output configuration, the CPU has distinct input and output instructions, in and out instructions. Input-output read or input-output write control lines are used. Only 16 address lines are used to address input-output. That is, only 64K input and 64K output devices can be used. Data transfer is possible only with AX, AL, and input-output. 1 MB memory is fully available to applications. Separate address bus is used. Extra hardware circuitry is required. Memory mapped input-output. In this configuration, same address space is used for both memory and input-output. There are no specific input-output instructions. It allows the computer to use the same instructions for both input-output transfers and memory transfers. MOV or other data transfer instructions can be used. Memory read-write control signals are used. 20 address lines are used to address the input-output. Data transfer is possible with any register. Limits the memory for user applications. Same address bus is used to address memory and input-output. No need of extra circuitry. Interface protocols. The GPIB or General Purpose Interface Bus or IEEE 488 bus is still one of the more popular and versatile interface standards available today. GPIB is widely used for enabling electronics test equipments to be controlled remotely, although it was also used in many other applications including general computer communications. Today, most bench electronics test equipment has either a GPIB option or are fitted with it as standard. Even though it has been surpassed by other technologies, it has become so much of a standard that even now it is fitted often as a standard. GPIB origins. Originally, GPIB was named HPIB. This is an abbreviated form of Hewlett-Packard Interface Bus, as it was originally introduced by HP for controlling their test equipment. Later, the test equipment arm of HP became a separate company with the name Agilent. In view of when it was first introduced, it has gained a number of other names over the years. GPIB has been adopted by a number of major institutions that have given it their numbers. The Institute of Electrical and Electronic Engineers in the USA have given it their specification number 488 in 1978, and as a result, it is sometimes referred to as the IEEE 488 bus or IEEE 488 bus. This defines the basic mechanical, electrical, and protocol parameters. The IEEE 488.2 standard, released in 1987, defines the related software specifications. GPIB devices communicate with other GPIB devices by sending device-dependent messages and interface messages through the interface system. Device-dependent messages, often called data or data messages, contain device-specific information such as programming instructions, measurement results, machine status, and data files. Interface messages manage the bus. Usually called commands or command messages, interface messages perform such functions as initializing the bus, addressing and unaddressing devices, and setting device modes for remote or local programming. GPIB devices can be talkers, listeners, and or controllers. A talker sends data messages to one or more listeners, which receives the data. The controller manages the flow of information on the GPIB by sending commands to all devices. A digital voltmeter, for example, is a talker and is also a listener. The role of the GPIB controller is comparable to the role of a computer CPU, but a better analogy is to compare the controller to the switching center of a city telephone system. The switching center controller monitors the communications network, GPIB. When the center notices that a party device wants to make a call, send a data message, it connects the caller, that is talker, to the receiver, listener. The controller usually addresses or enables a talker and a listener before the talker can send its message to the listener. After the message is transmitted, the controller may address other talkers and listeners. Advantages and disadvantages of GPIB. Advantages: simple and standard hardware interface. Interface present on many bench instruments. Rugged connectors used, although some insulation displacement cables appear occasionally. Possible to connect multiple instruments to a single controller. Disadvantages: bulky connectors. Cable reliability is poor, often as a result of the bulky cables. Low bandwidth, slow compared to more modern interfaces. Basic IEEE 422 does not mandate a command language SCPI used in later implementations, but not included on all instruments. FireWire. Apple Computer has included FireWire ports on all its computers since the introduction of the blue and white G3. FireWire is a bus or hardware protocol designed for the high-speed transmission of data between two peer-to-peer devices. It serves as a digital link between the connected devices, which allows for a better overall quality of transmission at the high speeds at which it operates. Apple originally developed FireWire in 1995, and several revisions later, other device manufacturers such as Sony now support the protocol. Why FireWire? High-quality multimedia sources require a high bandwidth bus for transport. FireWire, or IEEE 1394, its generic title, is just such a special purpose bus. IEEE 1394 is a hardware standard as well as a software standard for transporting data at 100, 200 or 400 Mbps. The 1394 protocol is very scalable and offers the following features. Provides for both asynchronous and isochronous applications. Allows access to vast amounts of memory mapped address space. Allows peer-to-peer hostless communication. The 1394 protocol supports both asynchronous and isochronous data transfers. Isochronous transfers are always broadcast in a one-to-one or one-to-many fashion. No error correction or retransmission is available for isochronous transfers. By design, up to 80% of the bus bandwidth can be used for isochronous transfers. Asynchronous transfers are targeted to a specific node with an explicit address. It is possible to have an error correcting protocol inserted at the acknowledgement step. Protocol layers. The 1394 specification defines 4 protocol layers: the physical layer, the link layer, the transaction layer, the serial bus management layer. FireWire, also called IEEE 1394 and iLink, is another popular connector for adding peripherals to your computer. FireWire is most often used to connect digital camcorders, external hard drives, and other devices that can benefit from the high transfer rates up to 480 Mbps supported by the FireWire connection. FireWire also has the advantage of being able to transfer power to the device through the same cable that does the data transfer. A disadvantage of FireWire is that cables tend to be more expensive. Not all PCs come factory equipped with FireWire ports. The Universal Serial Bus, USB, a specification developed by Compaq, Intel, Microsoft, and NEC, joined later by Hewlett-Packard, Lucent, and Philips. These companies formed the USB Implementers Forum Inc. as a non-profit corporation to publish the specifications and organize further development in USB. The aim of the USB-IF was to find a solution to the mixture of connection methods to the PC in use at the time. We had serial ports, parallel ports, keyboard and mouse connections, joystick ports, MIDI ports, and so on. And none of these satisfied the basic requirements of plug and play. Additionally, many of these ports made use of a limited pool of PC resources, such as hardware interrupts and DMA channels. So, the USB was developed as a new means to connect a large number of devices to the PC and eventually to replace the legacy ports. It was designed not to require specific interrupt or DMA resources and also to be hot pluggable. It was important that no special user knowledge would be required to install a new device, and all devices would be distinguishable from all other devices, such that the correct driver software was always automatically used. Data speeds. The USB specification defines 3 data speeds shown to the right. These speeds are the fundamental clocking rates of the system and as such do not represent possible throughput, which will always be lower as a result of protocol overheads. Low speed. This was intended for cheap, low data rate devices like mice. The low speed captive cable is thinner and more flexible than that required for full and high speed. Full speed. This was originally specified for all other devices. High speed. The high-speed additions to the specification were introduced in USB 2.0 as a response to the higher speed of FireWire. Infrared communication is a low-cost method of providing wireless point-to-point communication between two devices. The Infrared Data Association, often referred to as IRDA, was formed in 1994 to develop standard methods for communicating over short-range infrared transmissions. These standards have continued to evolve and gain in popularity. Now, a wide variety of devices implement the IRDA standard specification, including computers, printers, PDAs, cell phones, watches, and other instruments. Many members of Microchip's families of 16-bit and 32-bit microcontrollers provide native IRDA standard support through their UART modules. This greatly simplifies the hardware design. For demonstration and prototyping purposes, Microchip has created the IRDA PIC Tail Plus card AC164124 for use with Explorer 16 development board DM2400001. Two PICs can easily communicate with one another using serial communication. IR communication is a basic extension of this method which can be easily implemented with a microcontroller PIC through an IR encoder decoder, NDEC, and an IR transceiver. The NDEC and transceiver used in this example support serial IR, SIR data rate ranging from 9.6 kbps to 115.2 kbps. The typical range of the transceiver is nominally from 2 inches to 2 feet and extends upward of 12 feet. The PIC, NDEC and transceiver employed all support bidirectional use. However, when a transceiver is transmitting, it essentially blinds its receiver and therefore cannot attain true full duplex communication. Only half duplex was used with the transceiver taking turns transmitting and receiving. When transmitting, the PIC sends the serial format data to the NDEC, which encodes or modulates it bit by bit. This encoded data is then outputted as electrical pulses to the transceiver. The transceiver converts these electrical pulses to IR light pulses. When receiving, the transceiver receives IR light pulses data which are outputted as electrical pulses. The NDEC decodes or demodulates these electrical pulses with the data then being transmitted by the NDEC UART back to the receiving PIC. This modulation or demodulation method is performed in accordance with the IRDA standard. Radio connectivity. Radio connectivity is used to extend the range of a LAN or make it easy for users with laptops to connect to the LAN without the use of cabling. Wireless radio LANs require that an access point be placed on the network for the computers that wish to connect to the LAN. The distance that a computer can be from the access point and still connect to the LAN varies from wireless product to wireless product. Bluetooth. Bluetooth is a wireless technology standard for exchanging data over short distances using short wavelength UHF radio waves in the ISM band from 2.4 to 2.485 GHz from fixed and mobile devices and building personal area networks, PANs. Invented by telecom vendor Ericsson in 1994, it was originally conceived as a wireless alternative to RS-232 data cables. It can connect several devices, overcoming problems of synchronization. Bluetooth was standardized as IEEE 802.15.1, but the standard is no longer maintained. Bluetooth operates in the range of 2400 to 2483.5 MHz, including guard bands. This is in the globally unlicensed but not unregulated industrial, scientific, and medical ISM 2.4 GHz short-range radio frequency band. Bluetooth uses a radio technology called frequency hopping spread spectrum. The transmitted data are divided into packets, and each packet is transmitted on one of the 79 designated Bluetooth channels. Each channel has a bandwidth of 1 MHz. Bluetooth 4.0 uses 2 MHz spacing, which allows for 40 channels. The first channel starts at 2402 MHz and continues up to 2480 MHz in 1 MHz steps. It usually performs 1600 hops per second with adaptive frequency hopping, AFH enabled. Communication and connection. A master Bluetooth device can communicate with a maximum of 7 devices in a PicoNet. That is an ad hoc computer network using Bluetooth technology, though not all devices reach this maximum. The devices can switch roles by agreement, and the slave can become the master. For example, a headset initiating a connection to a phone will necessarily begin as master, as initiator of the connection, but may subsequently prefer to be slave. At any given time, data can be transferred between the master and one other device, except for the little used broadcast mode. The master chooses which slave device to address. Typically, it switches rapidly from one device to another in a round-robin fashion. Since it is the master that chooses which slave to address, whereas a slave is, in theory, supposed to listen in each receive slot, being a master is a lighter burden than being a slave. Being a master of 7 slaves is possible. Being a slave of more than one master is difficult. Bluetooth is a standard wire replacement communications protocol primarily designed for low power consumption with a short range based on low cost transceiver microchips in each device. Because the devices use a radio broadcast communication system, they do not have to be in visual line of sight of each other. However, a quasi-optical wireless path must be viable. The effective range varies due to propagation conditions, material coverage, production, sample variations, antenna configurations, and battery conditions. Most Bluetooth applications are indoor conditions, where attenuation of walls and signal fading due to signal reflections will cause the range to be far lower than the specified line of sight ranges of the Bluetooth products. Zigbee is a specification for a suite of high-level communication protocols used to create personal area networks built for small, low-power digital radios. Zigbee is based on an IEEE 802.15 standard. Though low-powered, Zigbee devices can transmit data over long distances by passing data through intermediate devices to reach more distant ones, creating a mesh network. That is, a network with no centralized control or high-power transmitter or receiver able to reach all of the network devices. The decentralized nature of such wireless ad hoc networks make them suitable for applications where a central node can't be relied upon. Zigbee is used in applications that require only a low data rate, long battery life, and secure networking. Zigbee has a defined rate of 250 kbits per second, best suited for periodic or intermittent data or a single signal transmission from a sensor or input device. Applications include wireless light switches, electrical meters with in-home displays, traffic management systems, and other consumer and industrial equipment that requires short-range wireless transfer of data at relatively low rates. The technology defined by the Zigbee specification is intended to be simpler and less expensive than other wireless personal area networks, WPANs, such as Bluetooth or Wi-Fi. Zigbee networks are secured by 128-bit symmetric encryption keys. In home automation applications, transmission distances range from 10 to 100 meters line of sight, depending on power output and environmental characteristics. Zigbee was conceived in 1998, standardized in 2003, and revised in 2006. The name refers to the waggle dance of honeybees after their return to the beehive. Comparison of wireless technologies. Zigbee was formally adopted in December 2004. is targeting control applications in industry which do not require high data rates but must have low power demand, low cost, and offer ease of use, remote controls, home automation, etc. Offers data rates of 250 kbits at 2.4 gigahertz, 40 kbps at 915 megahertz, and 20 kbps at 868 megahertz with a range of 10 to 100 meters. Currently offers 3 levels of security. Costs around half that of Bluetooth. Can network up to 256 devices. Has power requirements much less than Bluetooth. Uses star, tree, or mesh topology. Bluetooth is designed for voice and higher data rate applications. Also operates in the 2.4 gigahertz spectrum. Operates typically over a distance of 10 meters. Allows for 3-mode security. Has a range of 10 meters. Has power requirements of 40 to 100 megawatt per device. Can network up to 8 devices. The Zigbee protocol. It can be viewed as 3 separate layers, each with its own specific functions. The application layer and some of the functions of the Zigbee stack layer are usually controlled by a microcontroller such as a PIC chip. In a typical system, the IC contains circuitry to meet the requirements of the physical layer and a portion of the media access control hardware MAC. The remaining MAC functions, software MAC, may also be executed on the microcontroller. Conclusion. In this chapter, the user has covered the following aspects of techniques of connectivity and networking: interfacing, infrared connectivity, radio connectivity, controller area networks CAN, and local area interconnect network LIN, embedded system and internet.